Okay, so we're back with calculus. And like I said, calculus will march forward with the material. I'll try not to do it too quickly because we're all not with clear heads yet. Calculus is hard enough if your head is clear or not anyway. So, okay, I'm kidding, of course. Half kidding. That was the review session. Just a second, let me find the class number. So we're in 20 now. Lecture 20. Lecture 20. And I think we've calculated the derivative of sine of x and only that, or maybe the logarithm as well. Let me see, maybe we did the logarithm. Now I'm having
I think
flashback.
we talked about it, but
No, we did actually calculate it. Yeah, we calculated the derivative of the logarithm as well. Okay. And I'll need that limit that we calculated here. Because we will use it again in a few seconds. So remember that this limit is log base A of E, which is 1 over ln of A. Okay. So we have shown that the derivative of sine of x is actually the cosine of x. And we've shown the derivative, of log in the base A of x is 1 over x log natural logarithm of A. And specifically, the derivative of ln of A, the natural logarithm of x, is 1 over x. So we've seen that. Next, we will calculate the following important limit. It has to do with some derivative. We'll see it in a short while. But now we'll calculate the limit. What is the limit as x tends to 0 of a to the x minus 1 over x? So first of all, where does the numerator tends to?
zero.
Yes, because a to the 0 is 1, 1 minus 1 is 0. Where does the denominator tend to?
Also zero.
0. So now what you might say that we
Scream
should...
is L'Hopital.
Yeah, but it's silly because we need that limit in order to find the derivative. And that happens. I think that is the last time that's going to happen, that story. So we're not using L'Hopital for that reason. What we will do is a substitution of the variables. We'll define t to be a to the x minus 1. We'll define t to be a to the x minus 1. So as x goes to 0, where does t goes to?
To 1.
No, because t is a to the x minus 1.
Okay. Also zero.
Also
Yeah.
0. And also a to the x is 1 plus t. Therefore, x, what does it equal to? Who can know how to single extract x out of this equation?
The logarithm of something?
It's the logarithm of something, exactly, Tomas. We apply the logarithm to both sides. And so x is the logarithm in base a of 1 plus t. And why is this so helpful? Because then we get the limit as t tends to 0 in the language of the variable t of, in the numerator we simply get t, and in the denominator we get log in base of a of 1 plus t. But does that ring any bell? That's exactly the inverse of that. אנא רגע. לנון, למה אתה מתערב? אבל מי ביקש ממך? אני בשיעור, לנון. So the yellow part, let's use another color. The green expression is the limit of the inverse of the yellow expression, agreed? So what is that limit? Sammy, you're on mute. So I just sing you dance.
Ln A.
Yeah.
Or
Ln A.
1 over log A.
1 over ln A. 1 over log A of it. Yeah, but ln A is enough. Now, therefore, now with this limit over here, the limit is from here to ln of A, right? So now we can derive. Now we are ready to derive a to the power of x, the exponent. So the derivative of a to the power of x is the limit as h goes to 0 of a to the power of x plus h minus a to the x over h. That's the definition of the derivative. It's the limit of the slopes of the chords. Who can tell what the next step will be? Look at it algebraically. What should we do?
Take out a to the x.
Exactly. That's the limit as h goes to 0 of a to the x times a to the h minus 1 over h. But that should ring a bell. What is the limit of a to the h minus 1 over h when h tends to 0? That's exactly ln of a. So that equals a to the x times ln of a. Specifically, the derivative of e to the x is e to the x times ln of e, which is simply e to the x. Now we finished proving all you knew about Euler's constant from high school. We knew that it is 2.71 something. We've shown that a long time ago. Now we've also proved that it's the constant for which the derivative of the exponent equals to itself. And you see that it works for e. For any other number, you get the constant ln of a, which is different than 1 if a is not e. Any questions up until now? What elementary functions did we not derive yet?
Tangent.
Tangent. So first of all, tangent is sine of x over cosine of x. And once we learn how to derive a quotient, we will be able to derive tangent. What else? I'll help you. How about the square root of x? I think specifically I did derive the square root of x, but let's ignore the fact that I calculated directly. I might as well written the fourth root of x.
But didn't you say that there wasn't a derivative?
No, I did. I did derive square root of x as an example.
We didn't. We said there wasn't at 0.
At 0 it wasn't, yeah, but at any other x we derived it. I think it's a bad example to write the derivative of x. Okay, it's a bad thing. Let's give another example. What's x to the power of 7?
X.
We didn't derive that, right?
X to the power of x.
No, x to the power of x, that's actually something else. We'll talk about it as well. But I don't know, the 7 root of x, or x to the e. What about 1 over x? That's x to the power of -1. Where I'm hinting at, all these are specific, are specific cases of x to the a, which we will derive later. Okay. And I think that's it. These are the main thing. We have inverse of functions like arctan, arcsine. We'll do that later as well. So we're stopping for a bit with deriving elementary functions. Next, we wish to create or discover formulas or derivatives of I phrase myself differently what I'm trying to say. I'll articulate myself differently. Formulas for arithmetics of derivatives, meaning what is the derivative, for example, of f plus g? What is the derivative of f times G, and so forth. And so forth. Okay? So that's what we're going to do next. I'll write the rules. I'll prove some of them, not all. The rest are the ones I'll skip are usually easy. So I'll break it into a few theorems because the assumptions needed differ from one case to another. So all cases that have the same assumption, I will bunch together. I will gather to cluster together. So theorem 1 in that case, assume f and g are differentiable at x0 and consider a scalar c. Then c times f and f plus g and f times g are all differentiable at x0 and 1 the derivative of c times f at x0 is simply c times the derivative of x. The constant simply slips out. The derivative of the sum at x0 equals to the derivative of f at x0 times g at x0 plus f at x0 times the derivative of g at x0. And not true at all. Sorry, I confused it. I mixed it up with the multiplication. The derivative of the sum at x0 is simply the sum of the derivatives. Sorry. Do you agree about that? What do you mean? What do I mean? Do you agree? You obviously didn't see the proof, but you should be familiar from high school with these formulas. Yet in high school, you don't usually prove them, and we will prove them in a bit. Okay? So what I meant to ask is, do you have any questions before I move on?
Just to be sure, when c is just a scalar that doesn't have x, right?
Yeah, it's a constant, yeah. And now, as usual for me, I remember that I need to prove a theorem beforehand.
I think you made a mistake on the second line.
Why? Oh yeah. G, thanks. But beforehand, I need to prove a theorem. We will prove that any differentiable function is continuous at the same point. I'll phrase it mathematically in a bit, but you need to remember that differentiability hints, or how do you say in English the arrow? In mathematical logics, P arrow Q. How did you call it? You had a name for it. If P, then Q. Do you remember? Yeah, but what was the name, Sammy? This is not helpful. I remember you said some name. Whatever.
I don't remember calling anything. By conditionality.
But what? I didn't hear.
You want the name of the arrow or like what it actually means?
Yeah, if A then B, how would you say it in logics?
By
Remember?
conditionality.
How?
But I'll just type it.
Yeah, type it. I don't hear you well. It sounds wrong, but maybe I didn't. No, but not by conditionality. I just want one error, not two-sided error. I want to say that differentiability, in Hebrew we say we have a word gorer. It follows from. It so implies, yeah, that's the word I was looking for. Sorry, thank you. So differentiability implies. Wait, did you write something else? Yeah, implies. That's what I was looking for. Implies continuity, yet not the other way around. Who can tell me a continuous function which is not differentiable? You should be able. I gave you one. I told you this. What?
Absolute value of x.
Exactly. Thank you. And the absolute value of x is continuous at x equals 0, yet not differentiable at x equals 0. Okay, so that's an important thing to remember. And I'll prove now that differentiability implies continuity. So theorem, and I'll phrase it accurately. Theorem. Assume, sorry, f is differentiable at x0, then f is continuous at x0. And in order to prove that theorem, we must remember our definitions. We are given that the limit of the chords exists and is, meaning the derivative at x0 is the limit as h goes to, rather x, fx. X goes to x0 of f of x minus f of x0 over x minus x0. We need to prove that the limit as x go to x0 of f of x equals to f of x0. That's continuity. That's differentiability. That is continuity. So we need to prove that the distance between f of x and f of x0 goes to 0. Wouldn't it be nice? What's the wouldn't it be nice here? That's the limit I have. But what would I prefer to have here?
Wait, how did you make that step?
Which
You took
step?
away f of x of f of
From
x0
here to
from
here? From here to here?
how are we allowed How are we allowed to
Okay.
do that?
That's from a galaxy far, far away, long, long time ago. And I'll remind you. It's one of the first theorems we learn about sequences. And I believe showing you would jog your memory in that sense. I didn't phrase it in functions language, but it's the same due to Heine. Wait. That. The sequence AN tends to L if and only if the distance between AN and L tends to 0. Does that ring any bell, Sammy?
Right.
But that's exactly that. That's what I'm saying. Instead of saying that F goes to 5, it's equivalent to say that F minus 5 goes to 0. Okay? Okay. So again, I'm going back. That is what I have. And I'm going to apply the win principle. What would I prefer to have?
fx0 minus fx0.
No, that's like 0. That's too much. Look at the assumption we have. This is the numerator. We would like the denominator to be x minus x0. Agreed?
Mm-hmm.
But that's not what we have. So how do we fix it?
We multiply.
Yeah, by x minus x0. And that's the end of the proof. Why? Where does this tends to?
Fx minus fx0 over x.
No.
Ah,
That's the
okay.
derivative. And it is known that it is finite. Right? So this is some finite limit. Where does this tends to?
0.
0. So any finite number times 0 is
0.
0. That's the proof. Okay, short, nice proof. I always forget it. I'm always so excited once we define the derivatives to actually go to derived functions, but I need a simple theorem, important theorem within the proofs here. You will see when. Okay. So now we're back to arithmetics of limits. Parts 1 and 2, I will leave you as homework. They're rather easy. I will do 3. That's the interesting one, which is not completely trivial. Proof. We will prove claim number 3. So what is the derivative of f times g at x0? By definition, it's the limit as x goes to x0 of the product at x minus the product at x0 over x minus x0. And now the wouldn't it be nice is a bit harder, but we did same sort of steps again long time ago in a galaxy far, far away. Can anyone remember what would we prefer here? What would make this algebraically nice?
How is it called? The complement over the complement.
No, you mean the conjugate?
Yeah.
Minus plus? No, it will be squared. That's horrible. No, because I don't know what to do with f squared. It's be worse than what I have. That's what I mean. What else? What would you prefer to be in the numerator? Instead of fx0, gx0, what would have been a bit easier? So you can do some algebraic manipulation.
fx gx kind of? No.
If they're both x, then it's completely zero. But what
No.
can we do in between?
Make
One of them to be x?
Yes. fx gx0. That's the wouldn't it be nice here. And then we need to fix it, obviously. And we say plus fx gx0 minus fx0 gx0.
Is it not fx0 gx0 fx0 gx?
No, because I subtracted and added the exact same expression.
Got it. Okay.
And this is super helpful, and you'll see why. This is the limit as x goes to x0, not t0, x0, of. So from the first pair, what can we take out as a common factor? F of x. And what we are left with is g of x minus g of x0 over x minus x0. Plus, what is the common factor between the other two? G of x0 multiplied by f of x minus f of x0 over x minus x0. Do you agree with the algebra here?
Oh, that's nice.
Yes. Why is that nice? So first of all, f of x, what does that tend to?
F of x0.
Exactly, and that's the proof. That's why I'm getting I remember it, because in this proof I need the theorem above that f of x actually goes to f of x0. That the differentiability implies continuity. So I need it here. What about this expression? What is its limit?
The derivative.
The derivative of g
Definition of the derivative.
at x0. This is a constant, so the limit is the number itself. And this goes to the derivative of f. And this is hella cool. Does anyone still say hella? It's America anyway. And we get here f of x0 times g prime of x0 plus g of x0 times f prime of x0, which is exactly the theorem, maybe with a bit of a commutative rule applied. But that's that. Any questions so far?
Yeah, you said that the wouldn't it be nice was something that we'd seen already, but I don't remember seeing it.
Yeah, okay, then I'll show you where.
Oh wow.
It's
All
in
the way
limit
up.
of, no, first of all, it's not here yet, but it's in limit of sequences. That's the definition of a limit, the theorems, the arithmetics of limit of sequences, the very same trick. Let me find the arithmetics theorems. That's the 0, 1, still not that. That's the bounded one. That's the exercises, whatever. Class 6. I think it's gonna be here. By the way, that's the one I just shown you, Sami. And that's the product. AO here. See, very same trick. I added A and B. I had A and Bn, so I added An and B. One of the sequence I left, the other one I replaced by the limit. Okay?
What was this proving that if AN is
That's
bounded,
no, that's the arithmetic of limits. If An goes to A and Bn goes to B, then An times Bn goes to A times B. So it's arithmetic
right?
of product of limits, and now we do the arithmetic of products of derivatives. So in both cases, we start with a product. That's why the algebraic trick is similar. You see, it even looks the same. You have bounded times 0 plus bounded times 0. It's kind of the same, only you have a denominator here, which makes it the derivative instead. It's a philosophical question whether these little tricks are, I don't know, the actual meaning of reason to the theorem being true, but I don't think that matters much. I do think that these kind of, that's why, by the way, I cluster them all as win, because the idea of writing what you want and shaping reality around what you need is, I think, the one most important way of mathematical thinking that helps you in computer science, but in general. Because a lot of time, that's what you do. In computer science, I think something very similar to WIN is the concept of interfaces. You're saying, this is the class I want. Now let's start. Did you learn interfaces yet? You learn
Yeah.
object-oriented, right? So say, this is what I want. Now let's start thinking as to how can I make it happen. So that's a very mathematical and very important way of solving problems. And when you have similar problems, like here the product, then you have similar tricks. In general, I think object-oriented, even though it's the least formal computer science subject, I think it's one of the most mathematical. I use it a lot of time in my courses in mathematics and like a field. I don't remember if I told you, but the very definition of a field is again some sort of an interface, because I want a structure that follows these rules. And as long as it follows these rules, I will call it a field. It's again the same thing as implementing an interface. Okay, so that's that. We have the product. Next, can you care to guess what would be the next one that I will do?
Multiplication and division.
Multiplication I just did, so it won't be next. And
Yeah.
so
Addition
division,
one.
yeah, so division is a good not correct guess, because it is possible to do division next, but there is a neat trick to have division follow from other rules. So I skip division. What would be next after division?
Addition. Oh, after division.
Yeah, because we had addition, right? I didn't prove it, but I wrote it. I have addition, I have multiplication. What?
Exponentiation? No, but that doesn't make sense.
Exponentiation might have been nice, but there is a possibility to write a rule for it, but usually you do a certain trick. I will teach you that trick for exponentiation. So that's not the next one. What else?
Chain rule.
What operation between function there exists?
Oh, component.
Composition, yeah, the chain
Okay.
rule. You said chain rule. I didn't.
Aha!
In hindsight, I got it. You said the chain rule, but you're correct. I didn't. I had the data in my mind, but it wasn't. The neural network did not interpret it correctly. So okay, sorry. And that was geeky of me. The next theorem, assume that G is differentiable at x0 and assume that f is differentiable at g of x0.
Why do we use x0 as opposed to just x?
Come again?
Why do we use x0 as opposed to x?
Because x is like general, x0 is a specific one. Right, x is we do it since high school. Y and x are the variables that we use to describe the general connection between the x-axis and the y-axis. And usually, when we want a specific point, we call it either a or x0. So that's the reason.
So x0 is a specific point, but it's
Yeah,
generalized for all points.
yeah, that's what I'm saying. And sometimes I do use x when it's least confusing. Here, look at the limit. If I would have used x, then x could not tend to x, and then I would have to use the age version, which is not definitely horrible, but I prefer these proofs with the x goes to x0. So in any case, g is differentiable at x0, and f is differentiable at g of x0. Then the composition f compose g is differentiable at x0, and the derivative of the composition at x0 is is altogether the product of the derivatives. By the way, it seems the chain rule seems like the most complex rule, but it's actually the easiest rule. The reason that it seemed complex is because we multiply the derivatives, right? Think about it for a second. When we derived the product of two functions, we got this horrible formula, f times g prime plus g times f prime, right? Here, we actually get just a product of f and g. But the confusing part is that we derive the two functions at different points. We derive g at x0, and where do we derive the f?
F at g
G of
x0.
x0, exactly. So that's the confusing part. So it is altogether the product of the two derivatives, but at different points. Example, say G measure your velocity, your speed. Sorry. Yeah, אם זה עובד. Say G measure your location, then G prime is your velocity, speed. Say F measure the heat at your location. You are running towards, how do you write towards?
Towards
Like
Eh.
this?
TOWARDS without the H.
W,
That's fine.
like this, towards?
I think so.
Yeah, towards a fire. So, the composition G of F of X is the heat at your position, right? Because F says what is your, not exactly on, I use T, that's better, is the heat at your position at time T, right? Because F of T, oh, and sorry, I composed it the other way around, F of G. So G says where you're at times T, and F says what's the temperature given that location at a given location. So F of G of T is the heat at your position at times T. Now, say that you move at a rate of 2 meters per second, and say that the heat rise at 3 degrees per meter. So in 1 second, how many degrees will rise? The heat will rise how many degrees? Now read it and try to answer. Yes, Sammy. Will rise 6 degrees. That's the chain rule. That's the chain rule. It's simply the product of the rates of change. The difference is that the degrees, the variable is the location, and the location, its variable is the time. So these are different units even altogether, and different locations, different values. But it's simply the product of the rates of change. And that's not a proof, that's just a general explanation around the chain rule. So let's prove the chain rule. And I'll write that the theorem is the chain rule. Chain rule for one variable. It has versions, generalized version for a few variables, not part of this, the syllabus of this course. So prove, we will prove the theorem assuming G is 1-to-1, חד-חד ערכי, and if it's not a huge deal, but a huge distraction distraction from my x, because you waste most of the time of the proof proving it for this specific problem, and then you lose the big picture, and I don't wish for it to happen. So I'm assuming G is 1-to-1. I'll explain to you exactly where I use it. So we wish to derive the composition f of G at x0. So that's the limit as x goes to x0 of f of g of x minus f of g of x0 over x minus x0. Can anyone guess what would be the win here? What would be the nice? What would be nice? Wouldn't it be nice? Anyone guess? What can I change here that will make it simpler? This is the change of f. What should we divide it by? Say this is your second location, and this is your first location. What should we divide it by? What would be preferred to be written down here? So the difference...
G of x minus g of x0.
Yeah, exactly. That is what would we prefer. And we need to fix that. And we divide by x minus x0. And now you'll see something beautiful. Where does this tend to?
The derivative of G.
The derivative of G at x0, right? And where does this tends to? That's a bit more confusing.
The derivative of f
F at
Gx
Gx 0.
Yeah,
at
Gx
gx.
0, exactly. Because G of x, I'll write it, because G of x tends to G of x0. Because G is continuous, because G is differentiable. So I know that the numbers here, G of x tends to G of x0, and I divide the difference in f by the difference in its x-axis, in its domain. So I get the derivative of f at the point G of x0. That's exactly what's happening here. So altogether, we get the chain rule f prime of G at x0 times G prime at x0. Where did I use the G's 1-to-1? Hint, if G wasn't 1-to-1, then what would have happened here?
One to one. We
Answer that.
couldn't know. Like, we wouldn't be able to know the value of G at x is the same as G at x at 0.
No, that would be due to the continuity. It's worse, it's the other way around.
We'd have multiple values of the derivative of g.
That's not 1-to-1,
at
no.
x0.
If it's not 1-to-1, it is possible that G of x actually equals G of x0. And then what happens? We divide by 0. So because G is 1 to 1, I'm sure that this is not 0, and we are allowed to divide by it. If it's not 1 to 1, if it's actually 0, then you need to split into cases. The points where it is 0 and the points where it is not 0. So it's not that terrible. You get the same proof anyway. The same result, I mean, not the same proof. But it's not that interesting. מה זה? מה? לא יודעת? נקטרינה. תודה. Okay. So we have the chain rule. Now look at the following amazing thing. One of the best results. What is the derivative of x to the power of a? Did any of you ever seen how to derive x to the power of a by definition? Sometimes some teachers show it in high school. I'll take that as a no. And I'll note when we have f to the power of g, we should use the Ilan rule. I'm sorry, does not translate. I never thought whether it's translate. Let me think for a second.
3?
No, I don't think it translates. No, it is 3. Yes, no, I know that Ilan means something.
3 rule.
Yeah. It's funny because it's so close to log, which also is a type of a tree. You know, connected to a tree. It's not a type of tree. But, well, maybe you say maybe you think of one way to connect it. So what is the Ilan rule? The Ilan rule basically means to apply e to the power of lan of the expression you have. So first of all, mathematically, leave the wordplay aside. When we do lan and e to the lan, they cancel each other out, and that's actually equal. Algebraically, the two expressions are equal. Do you agree about that? Why is it called Ilan? E-lan, right? It's e to the power of lan. So there is a log here, but I'm not sure what to do with the e. What's an e log? I don't know. Okay, but that's close. In any case, it is completely not clear as to why it's helpful, but the reason it's helpful is because the log, the Ilan, we can call it the log rule. It's a good, okay. The log, it destroys the power in a good way, because we get here e to the power of a times log of x. Do you agree? So how does this help me calculate the derivative? This is the composition of e to the x that we got the composition of e to the x and a log x. Do you agree? That's the composition? So we can use the chain rule. What's the derivative of the outer function? What's the derivative of e to the x?
E to the x.
E to the x. So we are left with e to a times ln of x. That's the derivative of the outer function, sorry. And what do we need to multiply it by?
It's
The derivative of the inner function, right? A ln x. It's a over x. Agreed? But what? What is e to the power of a ln x? How can one simplify?
X to the a.
Exactly, that's x to the a. We're going back. So that's x to the a times a over x, which is equal to, drum roll,
Ax to the a minus 1.
exactly. X to the a over x. And that's the result we all know and love. Any questions? Another. Specifically, we'll see later why I'm pointing that out, that the derivative of 1 over x, which is the derivative of x to the power of minus 1, is minus 1 times x in the minus 2, which is minus 1 over x squared. One could have proven it directly by definition, but it's a result of this spectacular use of the rules we've proved. I like this so much because it's purely in high school level proof, right? It's not even a proof, it's just a calculation. The only ingenious part is the Ilan rule, using e to the power of ln to destroy the powers. And another example, what is the derivative of x to the power of x? Does anyone have any ideas as to how to calculate it?
Do we just do the chain rule twice?
No. What is the outer function and what is the inner function? The problem is that it is not clear at all that x to the x is a composition of functions, right? Because you're thinking x squared and 2 to the x, but there is no 2 here, and not just 2. There is no constant here. It's not a composition of two functions in a sense. Does anyone care to have another guess? Hint, it's just what I taught you and, and told you it's important to know. You have the power of two functions. Which rule should you apply?
The Ilan rule.
Exactly, the log rule. Well, right, I call it the log rule. So it's e to the ln of x to the x. Agreed? Which is e to the power of x log of x. Agreed? So what's the derivative of the outer function? It's the same. So we have e to the x log of x. And what do we need to multiply by?
The derivative of ln x.
Of x ln x. Agreed? And that's a smaller problem. And in general, calculating the derivative of a function which consists of arithmetic operations on trivial functions, elementary functions, is a recursive function in computer science. We simply figure it out whether it's an addition, a multiplication, or composition of known functions. Then we apply the correct formula. And in order to calculate the derivatives within the formula, we call the recursion function again. So the derivative of x ln x is a product, is the derivative of a product. So like before, e to the x ln x goes back to being x to the x, and x ln x is 1 times ln of x plus x times 1 over x, which altogether is x to the x times ln x plus 1. So now you know how to derive even exponent and exponentiation of functions, and even that is high school level stuff. The main trick is the log rule, the Ilan rule. Other than that, that's high school. Any questions so far?
Yeah.
Mm-hmm.
Can you just stay over the last line you just did?
What, this?
That line.
So this is, we applied the formula for multiplication. It's the derivative times the original plus the original times the derivative. So the derivative of x is 1 times ln plus the original, which is x, times the derivative that is 1 over x.
Oh.
And then x over x is 1.
Oh, all right.
Fine?
Never mind. I'm being stupid.
Okay. Suggestion to whomever does not know how. Okay, it's enough for today. See you guys.